Assalamualaikum warahmatullahi wabarakatuh, and a good day I bid to our panel today, Dr. Amir Azzi. My name is Zahirul Alimi bin Suraini and I am the lead engineer for Body Department of Underwater Drone. In this video, me and my friends from Body Department would like to present our project presentation for the making of underwater drones body for Mechanical Engineering Design 1 MEC531. First and foremost, let's take a look at the establishment of our project management. There are 4 points needed to be highlighted here, which are the goals of the project team management, project monitoring tools, and also the contingency plan. In this project, some of the goals include coming up with a proper design of underwater drones body that is suitable for many applications. Other than that, we also aim to keep track of costing in developing our product. Last but not least, ensuring that our underwater drones body able to contribute positively towards society and environmental impact. It is important to acknowledge the needs and expectations of customers to help us focusing on the overall purposes of the project. Obviously, the most basic requirement is a high quality body that is appropriate enough to be used. On top of that, a prepared manual that is well organized will also be much appreciated in assembling the product. Finally, a simple and proper analysis that is easy to understand will show the performance level of the underwater drone's body. As the lead engineer, I must make sure that the whole department members work together based on every member's task in order to ensure the progress of the project. I also have to communicate with other lead engineers from different departments such as chassis, propeller, and control system to validate every single work to assure no conflicts and errors occur.
Hi, Assalamualaikum. I'm Hanin Nashira. As a design engineer, I am responsible to conduct some researches, developing ideas in order to design the body parts of the product. Besides, I also need to think of the possible design solution of the body parts of the underwater drone by concerning the main body parts appear attractive, easy and safe to use with the help from the other engineer in the body department team.
Assalamualaikum and good morning, sir. I am Anwar bin Azan, a technical engineer under body department. My first job distribution is I am responsible for supporting the engineering team during the planning, development, design and troubleshooting process of the body drone. And second, I am responsible for finite element analysis and developing plan for greater efficiency in the body of the drone.
For my job description, I'm Amfidas bin Shamsulizam as the product engineer responsible on how the product will be manufactured and improving quality, safety and also reducing operating cost.
We will now move on the next section, which is the project description. Project description is basically an overview of our group will do throughout in this process of designing the body part of the underwater drone. The purpose of this project description is to put and creating a clear understanding of the project. In producing the desired body parts of the underwater drone, our team will go through 3 phases involving the phase 1, conceptual design, phase 2, embodiment design, and last but not least, phase 3 as a detailed design. So I will briefly explain the phases one by one on how we come up with the idea and the final design is decided. In phase 1, our team has done the defining problem phase where we did identify the focus group need through benchmarking, problem statement, design criteria and its design specification. Besides, we also collected the necessary data about the underwater drone's body design through textbook and some researches on the internet. Our team has brainstorming in doing the concept generation by exploring all the relationship in multi-dimensional problems. We also did the evaluation concept by using part chart as our selection method. We're completing our process stages by doing the detailed design by using the CATIA software.
In the early month of January, we have conducted a meeting through Discord application to discuss on the assembly of the product. The meeting was attended by every members from all departments and we found that several adjustments have to be made to further improve the quality of our work.
Moving on the next section, which is the project monitoring tools. To put it simplified, Gantt chart help us as a one team to know what's need to be done and when it needs to be done. Based on the Gantt chart that have been seen here, there are several activities we had planned for the whole semester. The first activity is the briefing about the subject by our lecturer Sir Razali Hassan. From then onwards up until the midterm break, we have done 80% of the phase 1, which is the conceptual design, including the problem identification, gathering information, literature review and the concept generation. We then continue finishing the conceptual design, and before we get to the special semester break due to the flood case, we have stepped into the phase 2, which is the embodiment design, when the technical specification was focused on here. Moving from there until the end of the semester, we continue the remaining phase, which is the phase 3 detailed design and phase 4 for the analysis design.
For contingency plan, the first one is expected problem that includes bad model and design error. The second one is a preparation, which we will design multiple products and be prepared for any change from other department. And the last one is execution, which to come out with different model and design specification and also improving it to the customer needs.
For the costing of this whole project, we have tabulated neatly the bill of material for references of our budget. There are several items necessary for us to purchase through online applications such as Shopee and Lazada, while some of the parts were made by 3D printing and have been planned to do so in the laboratory at UiTM's Mechanical Engineering Faculty later. The main body, which is the cylindrical acrylic tube, costs around 200 ringgit since it needs to be custom based on our reference, and the same goes for the front cover, which is the hemisphere acrylic dome, that costs about 80 ringgit. Other than that, fasteners and other joining tools include M4 screws, which takes about 40 ringgit 40 cent, and 5 bolts and nuts about 1 ringgit for 2 pieces, 60 ringgit for 1 flex glue, and 80 ringgit for a tape sealant. 3D printing nowadays costs about 1 ringgit per gram, and the total weight for our parts that were made by 3D printing may cost around 375 ringgit, which is the most expensive part so far. Those items are the front lid, body holder, body clamp, and also the back lid. There are also an indirect cost like the delivery charges that takes about 20 ringgit. Here is the stated list of reference for the parts that are needed to be purchased online. Therefore, the total estimation cost for the whole project is 780 ringgit. Problem statement. Imperfections in the body of the underwater drone, such as non-suitable material use, inaccurate dimensions, measurement and analysis calculated, may cause significant consequences and failures. For instance, a leakage happening inside the body and a fatal damage like a crack on the body due to high pressure of the water. Therefore, a suitable outline for the body design must be formed with a hydrodynamic design to achieve a desirable speed. Suitable materials that are strong enough to withstand the water pressure and appropriate dimensions for the user's convenience. There are 3 objectives. The first one is to design a body that is durable enough to withstand the water pressure deep under the water. The second one is to make sure the design of the body is suitable to be used together with other parts of underwater drones such as the chassis and the propeller. Last but not least is to ensure that the body's design have a compulsory space for all the electrical control system items to be stored safely and able to function properly inside the body.
For the first part, I want to present about the criteria of the body underwater drone. We have a total 4 criteria. First is the body should well put and strong to avoid any crack and able to withstand with water pressure of 15 kPa. The second is the body must have enough space to fit in all the necessary equipment which allow the system to function properly. And third is body able to function along with the chassis and the thrust power from the motor of the propeller. And lastly, the body is completely equipped with a proper and suitable joining method that prevent any leakage of water inside the body and loosen between any part. In this slide, I will present about specification of the body. The first specification is the cylindrical body of the underwater drone is mainly made out of acrylic, which allow the transparency effect to show some of the component part inside the body. For the second specification is the holder for the cylindrical body, which is produced by using 3D printing method, and selected material used is ASA. And the last specification is the dimension of the body. The weight of the body is around 800 grams, and the length is 450 mm, and the weight is 150 mm, and lastly, the height is 115 mm.
Next, I will cover the concept generation section by using the morphological chart. Concept generation is the most critical step in engineering design process. It is a procedure that starts with a customer requirement, target market, and it results in a different product concept design. Throughout in this section, we will be able to make a comparison between the main parts that are involved, which are the main body, front cover, types of joint used, and last but not least is tube holder. As we can see from the first row, which is the main body, there are several types of main body is chosen, involving PVC tube, aluminium tube, rectangular acrylic tube, and cylindrical acrylic tube. Our team has decided to choose cylindrical acrylic tube, which is the option 4 as our selected main body type, since acrylic has the highly resistant to variation in temperature. Thus, it is kind of suitable since our product will be dived in the sea. As we go through all of the criteria from the morphological chart, our team were able to choose the most suitable type of component of the body part. As conclusion, option 4 offers a suitable solution as its shapes of the main body can consider just nice and can still permit the whole execution of the engine system to boost the drone's performance. In this evaluation concept phase, our team has decided to use part chart as our tool to identify the most promising design concept. Part chart method will compare each concept relative to a datum concept and determine whether the concept in this question is better than, poorer than, or about the same as the preference concept. Several criteria and aspects have been compared in the tabulated data above, which include cost, safety, design ability, aesthetic, ergonomic, durability, and many more. Every criteria had been given a score for every product based on the specific weight using the symbol plus, minus, and 0. This is important to determine the product's ranking, and the highest rating of the product will be chosen. Through this analysis, concept 4 meet all the criteria of the body part that we want, and it obtained the highest score compared to the other concept. For the drawing of the component, I will briefly explain each component that had been used for our body parts. So basically, this is the full body drawing. We can see from the top view, front view, and the side view of the body part. This body part of the underwater drone consists of 9 parts that had been assembled, which are the main body, front lid, front cover, body holder for its connector, 2 types of sealant, body clamp, and the back leg. The dimension of the body part is quite similar to the normal and common body parts of the underwater drone in the market. We designed this body based on the millimeter measurement since it is much easier way to assume and build the design of the body part. This is the exploded view of the body part that we designed. An exploded view drawing shows the component of an object slightly separated by distance or suspended in surrounding space, in this case of 3-dimensional exploded diagram. So generally, this is the exploded view of the body part, which consists of 9 parts overall that have been assembled together, while there is also an attachment of bill of material for this part. Bill of material can be defined as the comprises of the assembly and parts required to construct the product. So, our bill of material is based on the drawing of the exploded view before. As we can see on the slide, our team has set the length of the body part, which is cylindrical acrylic, is to be 375 mm with the outer and the inner diameter of the cylindrical are 100 mm and 94 mm respectively. This length is set considering to the dimensional of the chassis. This is the drawing of the front lid of the component. The function of this front lid is to hold the hemisphere front cover and the edge of the cylindrical body. We set the dimensional for this front lid is suitable and compatible with the front cover as well as the main body by setting the length of it to be 140 mm. We also set the dimensional of the whole of the front lid in order for us to join the front lid part with the main body by utilizing the M4 screw with diameter of the 5 mm. Next is the drafting of the front cover that we designed. We use this front cover as it will connect the edge of the main cylindrical body. This front cover will prevent any water come into the main body since we concern with all the system component in the body need to avoid any leakage. We designed this front cover with the outer and the inner diameter of 95mm and 85mm respectively. As we moving forward, we will see this drafting of the body holder, which is one of the main part. The maximum length of this body holder was set to be 280mm with the width of 120mm. Since the function of the body holder is to hold the main body of the cylindrical acrylic, we inspired the shape of the body holder from the hexagon shape, which is kind of good and suitable for it to hold the main body. All of the dimensional we come out with is based on the other dimensional and position from the other parts. Thus, all the dimensional is suitable for each and every single part in the body holder. Same goes with the connector, we use the body holder to hold the part involved. For the body clamp, it has the similar function with the body holder where both of it will hold the main cylindrical body. The only difference is the position, where the body holder will be below on the main body, whereas the body clamp will be on the top of the main body. Both of these parts will be connected together through the suitable type of joining that will be further explained later on. All the dimension is properly set considering with the other parts. Last but not least, it is the back lid component. Our team has decided to design this part with the dimension of 100mm of its diameter, which is compatible with the diameter of the cylindrical main body. The function of this part is to close the back part in order to avoid any leakage happen when the underwater drone is dived into the sea.
For the dimension and weight, is shown here all of the parts dimension and weight. So the overall for the body of the underwater drone are 447.5mm for the length, 112.5 for the head and 160mm for its width. The total weight estimated is 825 grams.
For this slide, I want to present the material used for the body part. For the front cover and main body, we use ACRYLIC material. The main reason we choose ACRYLIC is because it is excellent in optical clarity and has transparency. Furthermore, it has high resistance in various temperatures where it can withstand up to 70 ton impact compared to ordinary glass. And for the last is it have half of weight of glass, an ideal for the precision machining process. The second material we use is ASA. This material for the production the body holder. Basically, the ASA has similar to ABS, but he has some improvement in terms of mechanical properties, superior aesthetics and UV resistance. The additional advantage of ASA is it has less wrapping tendency. It have a lower odor compared to other materials, and it has strength and is durable enough to withstand underwater pressure.
Types of joining method. Listed here are the parts involved: the cylinder, clamping flange, the front lid and the back cover lid. For the front lid, which we will be using bolt and nut. Bolt and nut is a non-permanent joint so that it's easy to assemble and disassemble the body for maintenance purpose. This allows the connection between the front cover and the body. M5 size will be used for the bolt and nut. For the front cover, we will connect with a super glue, which the product is the flex glue. It's a type of glue that can work on variety of surfaces and very strong at that, and also very waterproof. For the joint will enhance its waterproof by adding a sealing, and we will using a sealing tape. It's easy to use. This will add extra security to prevent water leak into the main body, which holds the control system. And for the cylinder clamping flange, screw will be used. This is the same as the bolt and nut, which is a non-permanent joint. It used to hold the connection between the cylinder body and the chassis of the underwater drone. And full size is used for the screw. And lastly, for the back cover lid, which is the main entrance for the control system of the underwater drone. This type of lid uses pressure to tighten it, so high water pressure will close the lid tightly when the drone enters the underwater. This lid does not use any joining such as screw, so it can easily be opened for maintenance purpose.
Here in the engineering analysis results, we will focus on two vital parts of the whole body, which are the main body and the front cover. For the main body, several assumptions and data have been stated, including the tube dimensions and the condition of water. By calculating the buoyancy force that we obtain to be 3.3526 Newton, we then able to calculate the density of the main body, which is 1166.93 kg per meter cube. In the static condition for the analysis, we would like to know how much is the hydrostatic pressure for both situations where the body is in fresh water and also the seawater. Obviously, the upward force is going to be equal to the downward force in order to set a static condition assumption. By using the formula of density and two different values of density for both freshwater and seawater, we come to the conclusion that hydrostatic pressure in seawater is indeed higher than freshwater at about 5 meter depth under the water. In dynamic condition, we observe a situation where the body will move in front direction. Noted that two vital assumptions have been made, which are the drag coefficient and the value of thrust from the motor in propellant. Using the equation of drag force, we get the value of the fluid friction to be 3.21 Newton when the body moves at the velocity of 1 meter per second. Further kinematics analysis tells us that the body takes around 0.015 seconds to accelerate from static condition of 0 meter per second velocity to dynamic condition with 1 meter per second velocity. The acceleration for that method is 66.975 meter per second square, and the body managed to cover a distance of 7.5 millimeter. Similarly with previous analysis, the front cover has a different value of drag coefficient since the shape is hemisphere. Its dimensions have also been clearly stated, and the value for the drag force is 2.9681 Newton.
Analysis for the joint. For the shear stress, we focus on the number of screws we'll be using, which is 16 screws. The amount it can withstand high water pressure is about 37,000 Newton. And for the tensile stress, it can withstand a force amount about 3,600 Newton.
For the safety factor, it is basically known as a method to display how much stronger a system is. We use this equation of ultimate load divided by the allowable load. Several assumptions have been made, including the thickness of the main body part to be 6 mm. Based on the safety factor of 1.2, we obtain the value for allowable load to be 69.5 megapascal after dividing it with the ultimate tensile strength for the acrylic, which is 83.4 megapascal.
Last part, I want to present finite element analysis. There are two parts of the body we analyze, which are the main body and front cover. There are two medium that we consider in the analysis. First, when the body in seawater, and second, when the body at freshwater. Moreover, the loading condition of the body also is considered, which are in static condition and dynamic condition. The density for freshwater we use is 997 kg per meter cube, while for the seawater is 1023 kg per meter cube, and the depth of the immerse for the both medium is at 5 meter. Let's see the image for the finite element analysis. For the first image, the condition of the main body is in static condition in freshwater. By referring to the image, we can see that the maximum of mixture stress for this state is 765 kilopascal. And the second image, static condition at seawater, we notice that the warm mixture stress value is higher compared to freshwater, which is 785 kilopascal. In the dynamic condition, There are a few forces are considered in the analysis, which are the drag force from water, thrust generated by propeller, and the acceleration of the main body. The value for drag force for main body is 3.21 Newton, the thrust is 30 Newton, and the acceleration is 66.975 meter per second squared. This acceleration we consider when the body accelerates from 0 until 1 meter per second. We can see the main body in the dynamic condition in fresh water. The main body is still in its original shape and no deformity occur. This slide shows the last condition for the main body part is analyzed in dynamic condition at seawater. From all the conditions in FEA analysis, we can see that the material ACRYLIC with the thickness of 6 mm that we selected for the main body is safe to use, because the FEA analysis result show that the main body part is not deformed in all conditions that we want. For last part is the front cover. Basically, the hydrostatic pressure applied is equal to the main body, but it has a differences in terms of the drag force when we analyze in dynamic condition. The value for drag force at the front cover is 2.968 Newton. For this analysis, we obtain that the Volt's missile stress is 236 kPa at fresh water and 242 kPa at seawater. And also, we can see that no deformity occur to the front cover. In conclusion, we can see that the material and dimension for the front cover that we choose are suitable for the condition that we want to run the underwater drone.